Okay,
Yeah.
so we wanted to go over the exercise of understanding what the time-ordered exponential means when, in particular, we're looking at solving for the evolution operator in the time-dependent Schrodinger equation. So I'll start with a time-independent case just to show you an analogous quantity, which looks like this. T psi equals h of psi, and h is time independent, right? So what you want is something that can take time, that can take psi of t to psi of t prime, right? So you want to solve for u. And it doesn't take long to check that u needs to satisfy its own little equation that has this form. So there's no way. It would have been h of t if this was time dependent, but now it's time independent, which means that really u is right.
Yeah.
So that's quite nice. So if we set t to 0, then this is just t power minus iht. So what happens if h depended on time now, right? So let's go over to that case. So what we're after is the solution to this equation. T u, and I'll take t prime to be 0 for now. This will be okay, but now you see h depends on t. Another simple property of this is that if I was evolving from, if I take u of 0, which is really u of 0 comma 0, then I should get 1, right? So this problem falls into a broader class of problems, right? And that very generally can be written in this way. Zero equals 1. Right?
Yeah.
So we can forget the context and ask, how do I solve this equation? Right? And it helps to note that I can write f of t really as
1 plus 1 integral.
the following, right? So what will it be, Pradyot?
Integral from 0 to t, which is like
Yeah.
this is the initial to whatever time you want, a of t. T prime, f of t prime dt. Yeah.
Exactly. Right, so we can check that if I were to take the time derivative of this, just bring the derivative under the integral sign, and I would get this, the above equation.
Yeah.
Right?
So you kind of do a recursive. Okay. Yeah.
Right. So from here, we can actually, well, you see there's an f on either side of this equation. So what's to stop us from saying that, well, f of t prime is also given by this expression, right? Except now I'm going to be putting t double prime here, double prime here, double prime here, t prime here, right? And then this just goes on.
Yeah.
So what we can do is say that now f of t, let's just put these steps together. I'll start slow so that, we get a sense for where we're going. 1 plus the integral from 0 to t. I don't like the primes because, you just have to proliferate them. Instead, I'll use t and t1 and so on. A of t1, right? F of t1, which equals 1 plus integral 0
T1.
t
Uh,
of
oh yeah, 0 to t, a of t1 of
yes
t1, and then you have, yeah, that's it.
t1 dt1,
Yeah.
right? You
Yes.
have
Yeah.
a of t1 dt1 plus integral.
The integral from 0 to t prime, and then
Mhm. Yeah. Wait a second. Let's see if we've
with
done this right. So we expanded f, the original f. The original f had a of t1 and f of t, right? But f of
yeah,
t1 starts with 1. So that's all we have here,
yeah,
right? So now what we do is we say this goes from 0 to t, right? We have dt1 integral. Okay, in principle, we should say that we have just f of t2 dt2.
yeah,
But now you see the pattern, right? I could then
yeah.
expand this again, right? So eventually what we're going to start seeing is something like this, where you had dt1, oh, sorry,
A of t1. Yeah.
0 to t, dt1, integral 0,
To t prime.
t1, dt2, it's a of t1, right? A of t2, because that's how f of t2
Yeah,
starts.
and then yeah.
And then you just keep doing this. And you notice how T1 precedes T2 precedes T3 in principle, right? And you nest these integrals with a pattern. So you have 0 to t, that's always the outer integral. Then you have 0 to t1, which is the next integral. Next integral will have 0 to t2.
So you have two terms coming out of each and every integral. So it is basically you're generating the next term whenever
Exactly.
you try to solve for the
Very good. So now what happens is that this is what we define to be the time ordered exponential of the integral from 0 t a of t.
Okay.
Now you see, if we had the Hamiltonian there, then that's what we would get for the quantum mechanical case, and that would be our
Yeah.
u of t. But this isn't restricted to quantum mechanics. In fact, if I was interested in a very different problem, right? If I was interested in a problem which told me that I have a curve, right? And the curve has a tangent vector v, right? So I have v of lambda. Lambda is a parameter along the curve.
Okay.
Lambda, right? I'll do this a bit in abstract notation because we don't want to be keeping track of
Yeah.
indices for something I haven't introduced.
Yeah.
C dot b of lambda, right? A lambda, C dot b of lambda. And again, I have a sense of where V naught began, right? So here, what would happen is that I would get, okay, let me go a little bit more slowly. V here is a vector, right? So yeah, So is A, but I won't just put this sign because it's a slightly more complicated. It could be a more complicated object. Um, so when you solve this equation, what you find is the expression for what's called a Wilson line. So what does this express? Well, this expresses parallel transport. So as you
Okay.
drag V along this curve, it's being transported through something called the connection A on
The
some
connection,
principal
yeah.
bundle. So what you get at the end of this is that this V at lambda equals what we call a Wilson line, right? Which is a function of A. And this Wilson line takes you from 0 to lambda, right? Of V at its initial position,
Okay. Okay.
right? And now the expression for the Wilson line is what's called the path-ordered exponential.
Okay.
Path-ordered exponential, the integral from 0 to a lambda dotted in the appropriate way with the line element along lambda.
Okay. Yeah.
Right.
So,
I've been a
oh,
bit abstract with indices here because we aren't talking about fiber bundles and principal bundles and so on before. But anyway, you see that this is the same class of problem, right?
yeah.
So you have a time ordering here, you have a path ordering here, but you have an ordered exponential. If I were to expand this, I would have connections appearing in the very same way.
Okay.
Right?
Yeah.
And
Yeah.
the analog of the time independent case here is really the abelian case. Right? If you have electromagnetism, then your Wilson line is just an exponential.
Okay. Oh, okay. Okay.
So this is very neat. And you can wonder, is there any situation where one meets the other, right? Like the time ordered exponential of quantum
In
mechanics, does
quantum
it ever
mechanics.
have anything to do with the parallel transport in gauge theory? It's a trick question. It occurs when you study the adiabatic theorem, um, and it leads into very fascinating physics of studied mostly in condensed matter. So it leads to what's called Berry phases,
Okay.
and we can do that too some other day. But yeah, basically the point I want to make was that you have this object that appears, right? This ordered exponential, and its origin is really coming from the trick you have here, right? This recursive trick, and just expanding it out. So yeah.
Yeah.
Do you have any questions?
Yeah. So, just one thing I think, like it would be good to kind of, you know, clarify the first thing, like the first, like how you get it, how you get the integral from you have an integral that is dependent on f, and then you
Yeah.
just take the f out, right? So,
Oh,
yeah,
you mean how do you go from this line to this line?
yeah.
Well, it's really a trick. I mean, all you're really doing is rephrasing
No,
a differential equation.
not putting the derivative the other side, but when you're actually talking about the f,
Mhm.
which is dependent on t prime,
Yeah,
okay, and here in the integral, we like if you go to the last line, so we
yeah,
see that f is dependent on t prime, and
yeah.
then okay, yeah, okay, so you say that f is like it depends only on a's at the end of the day,
Yeah.
right? Okay.
Yeah. Yeah.
That
Exactly.
basically like you're setting up f in terms of a's only, so
Yeah.
you're kind of yeah, good. All right.
Yeah. That's the
Yeah,
point. That's the point. And you see, when you have the Schrodinger equation, it makes sense that the Hamiltonian is the only thing that's carrying you. So there, A would be minus IH, right? So then the
right,
Hamiltonian is the only thing carrying you from one time to another. So
right.
that makes perfect sense. And similarly with parallel transport and the connection. The connection's what's carrying you from one um, point in the bundle to the other, carrying vectors essentially. So yeah, um,
Just
if
pause
you're
the
satisfied.
recording.